Welcome to Unit 7, Cartesian Vectors, Lesson 6, Application of the Dot Product and Cross Product. So we're going to do 4 examples. Please ignore the numbering because the numbering is way off. It doesn't go in order. And we're also missing example 2. But the first one we're going to do is torque. And torque is a measure of force acting upon an object, causing it to rotate. So the object rotates around what we call the fulcrum point. So this is center of rotation. The arm, so this is the length of the object you're using to rotate, and the vector always goes out like that. So that vector, the arm vector, always goes out, and then we've got the force which we're applying to the object, and then the angle between the force we're pushing at, and also the object we're pushing on to rotate the fulcrum. So here we go. Here's the first example. A wrench is used to tighten a bolt. A 600 Newton force is applied in a clockwise direction at 80 degrees to the handle, 20 centimeters from the center of the bolt. So we've got this. So here is our arm. That, of course, is our fulcrum. And we're pushing at an 80-degree angle. So we're pushing like this, where this angle here is 80 degrees. This right here, the force we're pushing at is 60 newtons. And then, of course, this guy here, this is 20 centimeters. Now, because torque is measured in Newton meters, we actually have to convert this to, meters. So this is really 0.2 meters. So how do we do this? What we're going to do is we're going to put the vectors tail to tail. Why? Because when we want to, this formula here is actually the cross product. So I'm going to put that vector tail to tail. So I'm going to move this guy here, move it down here so the vectors are tail to tail. So this is still, of course, 60 newtons. Using Z pattern, this angle here is also 80. And so now I can use my torque formula. So the magnitude of the torque, and torque is tau, which is a Greek letter for T. So we have magnitude of R, which is the length of the arm, times magnitude of the force, and sine theta, which is the angle between the tails of the two vectors. So here I'm going to have R, so it's going to be 0.2 times 60 times sine of the angle between it, so 80. And so here I'm going to get, put this in my calculator, I get 11.8 Newton meters. And there we go. Now what direction does this go in? So again, because the arm is always first and then the force is second, so my arm will be my index. So when I do this, tau is equal to, oops, let me fix that, sorry. So I have here tau is equal to magnitude of R, magnitude of F, sine theta, and then we also have the normal here at the end. So this is my, first one is always my index. The second one is my middle. So I'm going to have index middle, and so if my index is along here, my middle finger is along here, I can see that the direction is going into, so this is going to be into. So that means if my thumb is going into the page, that means that the bolt is being tightened. So therefore, since the direction is this, the bolt is going into the page and being tightened. And there we go. So the next example looks like this, mechanical work done. So my mechanical work done is just my dot product. So it's either this formula here if it's Cartesian vectors, or it is this formula here if it is geometric vectors. So here we can see we've got Cartesian vectors, so we're going to use this formula here. The force with units in newtons and defined by F and acts upon an object displacement of this. So this is my force, this is my displacement. So I know work done for part A is equal to F dot S. So here we go. I'm going to have 300 times 3 plus 700 times 1 plus 500 times 12, which will give me a total of 7,600. So therefore, 7,600 joules of work is being performed in the direction of travel. All right, part B. Part B says determine the work done against gravity, which is in the direction of the negative z-axis. So for this one, I am going to do my direction. So my direction is this, and since I just want it in terms of just my against gravity, and gravity is a z-axis, so I only really want that coordinate there. So my s is actually going to be 0, 0, because these two vectors don't affect gravity, but this one does, because this is my vertical component, that z. So I'm going to have work against gravity will be equal to F dot S again, but with my new S. So this is actually going to be equal to 300 times 0 plus 700 times 0 plus 500 times 12. So this is actually equal to 6,000 joules. So that's going to be the work done against gravity, so going up, where gravity is going down. Therefore, work done against gravity is 6,000 joules. Therefore, work against gravity is 6,000 joules. All right, projection. So here we go. We've done this before, but now we're in 3 space. So I want the projection and its magnitude. So if I want the projection of u on v, this is actually equal to u dot v over v dot v times the vector v. So I'm going to find that out. So here I'm going to have, this is going to be a lot of fun, so I'm going to have here u dot v is going to be 4 times 2, or times 6, sorry. 4 times 6 plus 2 times 3 plus 7 times 8 all over, and here we go, v dot v, so I'm going to have here 6 times 6 plus 3 times 3 plus 8 times 8, and this is all times the vector v, which is going to be 6, 3, 8. So this is going to give me, this is my calculator, I get 86 over 119, or 109, sorry, times 6, 3, 8, and if I multiply this in, I get 516 over 109, comma, 258 over 109, comma, and then finally I get 688 over 109. All right, so that is the projection of U on V. Now I want the magnitude. So if I want the magnitude here, I am simply just going to take this guy here and find its magnitude. So I want the projection, the magnitude of the projection of U on V. So I'm going to have here the square root of, this is going to be a lot of fun. Oops. 516 over 109 squared plus 258 over 109 squared plus 688 over 109 squared. And here I'm going to get a total of approximately 8.2 units. All right, last example. This is volume of the parallelepiped. So the volume of the parallelepiped is over here. It is this. By the way, this guy here is a three-dimensional shape, so it's a parallelogram, but it's really a parallelogram prism. That's really what it is. So it's a parallelepiped. To find the volume, it's A dot B cross C. It doesn't matter which one A and B cross C is, as long as you dot to and cross it. So do we do dot product or cross product first? Well, if we dot product first, we get a scalar, and you cannot do a scalar across a vector, so you always have to do the cross product first. So if I want here, the volume is equal to U dot V, cross it with W. So I've got to find the magnitude. So I've got to do here, I'm going to do V cross W. By the way, this is a good communication question. Why'd you do the dot product before the cross product? And I explained it briefly before. So here we go. I'm going to have I, J, K, I, J, K, and here I'm going to have, write my V vector first, so 2, 5, 6, 2, 5, 6, and then I'm going to write my W vector next, 10, negative 3, and negative 14, 10, negative 3, negative 14. Oh dear, these are getting close, so I'm going to do this and this, and I'm going to do this minus this, and then I'm finally going to do this minus this. All right, so V cross W, here we go. V cross W will give me the vector 5 times negative 14 is negative 70, plus, because I've got a negative here, plus 18, comma, 6 times 10 is 60, minus, that's actually plus here, 28, and then finally I'm going to have 2 times negative 3 is negative 6, minus 50, so my vector here will be, my cross product will be negative 52, 88, and negative 56. So that is V cross W. So now once I get V cross W, I want to dot it. So now I'm going to do a little space here. U dot V cross W. So this is going to be equal to, I'm going to take my vector U, so it's going to be 4 times it by the first coordinate of V cross W plus the middle coordinate of U, so it's 3 times the middle coordinate, which is 88, plus 1 times the last coordinate, so 56, negative 56, sorry. And so here, if I do this, I'm going to get negative 52, but again, I want the magnitude, so the magnitude of U dot V cross W is just equal to the magnitude of negative 52, which actually gives me 52 units, and because it's a three-dimensional shape, it's actually the volume, so it's going to be 52 units cubed, and so that is the volume of my parallelopiped.